So first thing we're going to talk about today is average rate of change. We should know what average rate of change is. Average rate of change, just fancy words for what? For slope, right? Yep. So just a fancy word for slope. So if we're looking for the average rate of change of the function f of x equals x cubed minus x on the interval from -1 to 3, we got to figure out what f of -1 is. What's f of -1? 0. And what's f of 3? Should be 24. And so all we got to do is y2 minus y1 over x2 minus x1 gives us 24 over 4, or 6. Okay. Everybody good with that? Average rate of change, not a calculus thing, like a pre-algebra thing, but sometimes they ask you for average rate of change on the AP test just because they want to see if you can differentiate between that and the average value theorem for integrals and the mean value theorem for derivatives and all that fun stuff. So the other reason it's important is because it helps us to develop this thing called the difference quotient that you should be familiar with. The difference quotient is f of x plus h minus f of x all over h. Right? So if we have 2 points on a function and we're looking for the average rate between them, and this point is x f of x, and this distance here is h, then that would make this other point x plus h and f of x plus h. And so the average rate of change between the two would be f of x plus h minus f of x all over x plus h minus x, or just f of x plus h minus f of x all over h. And that formula, the difference quotient, as a slope formula, should be pretty familiar to you because that's what we use to come up with the limit definition of the derivative, right? Everybody remember that from last year? Hopefully so. All right, so first off, we're going to find a secant line. We remember what a secant line is? What's a secant line? Secant line is just a line that, yeah, it indicates the average rate of change between two different points on a curve, right? It's just a line that goes through 2 points rather than being tangent, which touches at just 1 point. A secant line goes through it at 2 points. So we're going to find the slope of the secant line through any 2 points of the graph of f of x, which is x cubed plus 2x minus 1. So to find the slope of the secant line, we need to do f of x plus h minus f of x over h. So what's x plus h, or what's f of x plus h? That'd be x plus h cubed plus 2 times x plus h minus 1, and then we'll subtract f of x all over h. Everybody good with that so far? Okay, and then we'll expand it out and simplify. So x plus h cubed using the binomial theorem gives us x cubed plus 3x squared h plus 3x h squared plus h cubed plus 2x plus 2h minus 1, and then minus x cubed minus 2x plus 1 all over h. And if you remember from last year, hopefully you'll note that all of the terms that don't have an h in them in the numerator should cancel out. So x cubed and a minus x cubed, and 2x minus 1 plus 1. And then we can divide each of these, which have an h, by the h, giving us 3x squared plus 3xh plus h squared plus 2. Right? And that represents the slope of the secant line through any 2 points on the graph, where x is the first point and h is the difference between the first point and the second point. So if I was looking for the difference in the, or if I was looking for the slope of the secant line between the points at x equals 0 and x equals 2, we just plug in the 0, 3 times 0 squared plus 3 times 0, and we have to find h. So if we're going from 0 to 2, that tells us that h is 2. So plus 2 squared plus 2 would give us 6. So the slope of that secant line is 6. Everybody good with that? 1 second. I gotta help my kid with something here. All right, everybody good with that? Everybody okay with finding that average rate of change?
Mr. Bachelor?
Yeah.
So when you're plugging in x, you only have to plug in one of the points?
Yeah, you plug in the first one, and then the h value is the difference between the first and the second.
Okay.
Yep. So if I was looking for, you know, the slope between x equals 1 and x equals 7, I'd plug in 1 for x and then 6 for h, because the difference between 1 and 7 is 6. Good?
Yes.
All right, cool. Let's see if we could do it with something like 1 over x squared. Just to sort of remind ourselves how these work. So we're going to do f of x plus h, 1 over x plus h squared minus 1 over x squared all over h. And how are we going to simplify this complex fraction? How do we simplify this complex fraction? Okay. Common denominators. Good, thank you, Ashley. So multiply this one by x squared over x squared, and multiply this one by x plus h squared over x plus h squared. And we'll simplify that out. We got x squared minus x plus h squared, which is x squared plus 2xh plus h squared. And in the denominator, we've got x squared and we've got x plus h squared. And then that's all over h. But if I make this h as an h over 1 and multiply by the reciprocal, that h just goes into the denominator also. So then we'll subtract. The x squared minus the x squared will cancel out. And we're just left with a negative 2xh minus h squared over x squared times x plus h squared times h. So far, good? Hopefully. And then we can divide both the numerator and the denominator by h to give us negative 2x minus h over x squared times x plus h squared. And so once again, if we were looking for the slope of the secant line through the points, let's say we wanted to go from x equals 1 to x equals 3, our h value would be 2. We'd plug in 1 for x and 2 for h, so we get negative 2 minus 2 over 1 times 3 squared. Easy enough? Any issues with that? All right, so then the question is, what happens as we take our interval of h? One second, I'll go back to that, Molly. With my numerator, you're talking about the negative 2x h minus h squared. I divided it by the h that was in the denominator. So I factored an h out of it and canceled it with the h in the denominator. Well, x squared minus the x squared is 0, and then minus a 2xh, and then minus an h squared. Good? Yeah, okay. All right. So all the secant line stuff is great. It's, you know, sort of interesting to see that we can write a formula that represents the slope between the 2 points on any points on your graph. But the real reason why we're doing this is because we want to be able to shrink the interval of h all the way down to 0 and evaluate the average rate of change when that distance is 0. And what happens when we try to evaluate the average rate of change on that interval when h is 0? Well, we can't do it, right? Because if you look back at all of these problems, initially we had, you know, 0 over 0 if we did that, which becomes a problem. So first off, what does that make our secant line turn into? If the interval between the points is 0, we're no longer touching at 2 points. We should only be touching at just 1 point, which should make this a tangent line. So this turns our secant line into a tangent line. And now what we're doing, if we're able to evaluate that average rate of change, is we're finding the slope of the tangent line. And so the way we're going to have to do that, since we can't shrink the interval of h down to 0, because in our difference quotient, right, our difference quotient of f of x plus h minus f of x over h, that means we're going to be dividing by 0. So what we'll do is we'll take the limit as h approaches 0 of f of x plus h minus f of x all over h. And as we know, that's the slope of the tangent line at any given point at x. And this is the derivative of a function, right? Everybody good with that? This is where the derivative, which is the slope of the tangent line, comes from. Hopefully so. So let's use that limit as h approaches 0 of the difference quotient to find the equation of the tangent line to this function x squared plus x at x equals 3. Now I know you can all do this by taking the derivative, but we're going to do it once or twice without the actual taking of the derivative before we start doing that in a few minutes. And we'll give you guys one short assignment where you need to use this limit definition to find derivatives. But after that, you'll be able to use regular methods the whole way through. So we're going to find the limit as h approaches 0 of f of x plus h, which should be x plus h squared plus x plus h minus x squared plus x all over h. And we'll expand that out. Not sure why I decided to write that in the same line, but I did. And the minus x squared and the plus x squared will cancel, and the plus x and the minus x will cancel. And we've got the limit as h approaches 0 of 2xh plus h squared plus h all over h. H, and h can factor out and cancel with the h in the denominator, which gives us the limit as h approaches 0 of 2x plus h plus 1, which is just 2x plus 1. As h goes towards 0. Everybody good with that? Should have known already that that was the derivative of x squared plus x, but we can show it using the limit. And then if we want to evaluate that For the tangent, the equation of the tangent line, we need to have the point at x equals 3. So what's f of 3? F of 3 is 12. And we also need to evaluate this at x equals 3, which is 7. So we can write it in any form you really want. I'll use point slope form. Y minus 12 equals 7 times x minus 3. And you can put it into slope intercept if you want, but there's never any reason to go and do that, unless they specifically ask you to. Everybody good with that? And we could see, what was it, y minus 12 equals 7 times x minus 3, I think. That if we look at this at x equals 3, which is sort of hard to do here, but at x equals 3, right here, that's our tangent line at 312. The blue line is to the right of our parabola, touches at 312, and then is still at the right of our parabola afterwards. So that's our tangent line. Everybody good there? All right. So now we want to find all of the instances of when the slope of this tangent line for 1 over x is negative 1/4, and we're going to use a limit to do that. So what's our first step? Using the limit as h approaches 0 of our difference quotient, so 1 over x plus h minus 1 over x all over h. And once again, for a complex fraction, what do we need to do to simplify it down? We need to get a common denominator, right? Yep, good. So multiply by x over x. And multiply by x plus h over x plus h to get your common denominator there. It's all over h. And the x minus the x goes away, but the x minus the h becomes that negative h. So be extra careful about making sure you distribute that negative sign to both the x and the h over here. So we've got negative h over x times x plus h. And we have this thing is all over h, but I could write that as h over 1, take the reciprocal and multiply, and that h goes into the denominator. All right, we'll cancel. And as h goes to 0, this becomes negative 1 over x squared. Everybody good with that? We should have known that's the derivative of 1 over x just by using, you know, power rule or quotient rule or reciprocal rule, any of those. But everybody good with that, in that method? So we want to know when is that slope. So when is the slope of negative 1 over x squared equal to negative 1/4? Well, the negatives cancel. And if I cross multiply, that gives me x squared equals 4. So that would be at x equals positive or negative 2. Any questions or issues on that? All right, we recall what a normal line is. So we know a tangent line touches in one point. A normal line is the line that is perpendicular to the tangent at the point of tangency. So we want to write the equation of the normal line to f of x equals x squared plus 1 over x at x equals 1. first thing we need to do is find what? What do we need to find the equation of a line? We need two things. To find the equation of a line, we need to have a point and we need to have a slope. So our point is going to be the point 1 comma f of 1. So what's f of 1? Looks like it's 2. So we're looking at the point 1 comma 2. So we got our point. Now we just need the slope. And if we're looking for the normal line, we know it's perpendicular to the tangent line. So we can use the limit as h approaches 0 of x plus h squared plus 1 over x plus h minus x squared plus 1 over x all over h. Everybody good with that? So that's going to give us the limit as h approaches 0 of x squared plus 2xh plus h squared. I'm going to do this minus x squared first, and then I've got a plus 1 over x plus h and a minus 1 over x, and it's all over h. Getting a common denominator for all of this is going to be a pain, so it makes a little bit more sense to separate it into two different limits. And we can also cancel out our x squareds here. So the limit as h approaches 0 of 2xh plus h squared over h plus the limit as h approaches 0 of, and then this one will get a common denominator, just like we did before. And the first piece of it becomes what? H's cancel, and as h goes towards 0, that just becomes 2x. And we already did this one a little bit ago. So what did this one come out to be? Should be minus 1 over x squared. Everybody good with that? Which we will evaluate at x equals 1. And that tells us that the slope is 2 minus 1, or our slope is 1. And using point slope form, we got y minus 2 equals 1 times x minus 1. Oh, yeah, 2x. I think I said 2x. Sorry. Maybe I didn't say 2x, but yeah, 2x minus 1 over x squared. Which doesn't change our answer, but yeah, definitely 2x. Any questions on that? All right, last one we're going to do here using the limit notation. Figure it's good to do one with square root also. So f of x equals root x, and we want the normal line. We didn't find the normal line here, did we? That's my fault. Just realized this said normal line. We found the tangent line, which means our slope should have been -1. And we should put a negative in front of that because we're looking for the normal line, not the tangent line. Got ahead of myself there. All right. So same thing here. We want the equation of the tangent line and the normal line for this one for f of x at x equals 4 with f of x equal to root x. So first off, the point is 4 comma f of 4. F of 4 is 2. So we're looking at the point 4, 2. And we want to find the limit as h approaches 0 of f of x plus h minus f of x over h. And that's 0 over 0. So how are we going to simplify that down? Any ideas on how we're going to simplify that down? Oh, there we go. Somebody's saying something. Yeah, multiplying by the conjugate. So we're going to multiply this by square root of x plus h plus square root of x on both the top and the bottom. Which in the denominator gives us root x plus h, or sorry, in the numerator gives us root x plus h times root x plus h, which is just x plus h. And then root x plus h times root x, and then minus root x times root x plus h will cancel, and then we end up with minus root x times root x, or just minus x. And in the denominator, h times root x plus h plus root x. X's cancel, h's cancel, and we've got the limit as h approaches 0 of 1 over root x plus h plus root x. As h goes to 0, that's just root x plus root x, or 1 over 2 root x, which we should know is the derivative of the square root of x. We'll need to evaluate that at x equals 4, which gives us, for the tangent line, a slope of 1/4, and take the reciprocal of it. For the normal line, should be a slope of -4, and it'd be y minus 2 equals 1/4 times x minus 4 for our tangent line, and y minus 2 equals -4 times x minus 4 for our normal line. Everybody good with that? Everybody remember how painful all of that was? And happy that we only spend a few minutes doing it this year? All right, everybody good there? So after class is done today, I'm going to put up, I don't know, it's like 4 or 5 problems like this for you to find the derivatives using the limit definition. But then after that, all you need to be able to do really is recognize when they're writing them out in this form so that you can just take a derivative. We'll talk about that another day. So let's move on. Starting with the basic ideas for our derivatives and how we wrote out some of the derivative formulas. So first one we need to know is that the derivative of constant is always 0. It should make sense because if our function is a constant, then f of x plus h is the same as f of x. They're both just that same constant, and the constant minus the constant in the numerator is 0. We get 0 over h, or just 0. The derivative of any constant is 0. Everybody good with that? All right, now the one that's a little bit more difficult. Use the power rule. All right, hold on one second while you take a look at that and remember how we proved the power rule. Sorry about that. Had to deal with my children for a moment. So if we're looking for the derivative of f of x equals x to the n, then we'll take the limit as h approaches 0 of x plus h to the n minus x to the n over h. And so I've expanded all that out using the binomial theorem. But the important thing here is that we'll note that just like all the other ones we did, the x to the n and the minus x to the n cancel out. And every other term in it has an h in it. So we'll factor out that h and divide it by this h, which will leave us with nx to the n minus 1 plus some term with an h plus some other term with an h squared, and so on. And all those other terms will have h's in them. And so as h goes to 0, that goes to 0, and that goes to 0, and that goes to 0, and all that's left is n times x to the n minus 1, which is our power rule that we should know. Everybody's good with the power rule, yeah? And remembers where it comes from now? Okay. So real quickly, what's the derivative of x to the 7th? You can just unmute yourself and say it, or you can type it, I guess, if you want, but it seems like saying it would be quicker. 7x to the 6th, right? 7x to the 6th. What about x to the 4th? Should be 4x cubed. X to the 50th should be 50x to the 49th. Easy enough. Everybody good with all of that, right? Shouldn't be a problem. We know that it can be applied beyond just whole numbers, right? Any real number this can be used for. So x to the negative 1 should become negative 1x to the negative 2, or as we saw before, negative 1 over x squared. Yep. X to the 3 halves should become 3 halves x to the 1 half, or 3 root x over 2. X to the negative 4 should become negative 4x to the negative 5, or negative 4 over x to the 5th. And root x, which we did just a minute ago, that's the same as x to the 1 half, so that should become 1 half x to the negative 1 half, or 1 over 2 root x. Okay. Everybody good with all of that? Power rule, simple, straightforward, easy. Okay. So what should this one be? Two-thirds x to the negative 1/3 minus 12x to the negative 4. Good? And this bottom one should be x to the negative 4/5 plus 10x to the negative 6 plus 6x cubed. Easy and straightforward. All right, you guys do these two real quick while I go deal with my children again. I'll be back in a second, sorry. Sorry about that. Luckily, you can't all hear me yelling at my children. I don't think, right? I was muted, wasn't I? Oh, good. See, I figure sometimes, even if I'm muted, if I'm yelling loud enough, you can probably still hear. So our root x should become what? 1 over 2 root x, that's the rule that we should know. Our 5/4 roots of x cubed, that's x to the 3/4. So if this is 5x to the 3/4, that should become what? 15/4 x to the negative 1/4. And then this one is minus 1, or x to the 1/10, so it should become minus 1/10 x to the negative 9/10. Everybody good there? No, Delphine, you can leave your answers with negative exponents. That's totally fine. You could have written this one as 1/2 x to the negative 1/2 if you wanted. I just, we have the rule for root x memorized, so that's why I left that one this way and the other ones as negative. But either way, it's fine. And this one, this is x to the negative 1/2, so that will become negative 1/2 x to the negative 3/2 plus 15x squared. Everybody good? Any issues there? All right. If we want to find the first 4 derivatives, we got f prime equals 4x to the 3/2 is our first one, is f, so that should become 6x to the 1/2. What should our second derivative be? Second one should be 3x to the negative 1/2. Third derivative should be negative 3/2 x to the negative 3/2. And our fourth derivative should be 9/4 x to the negative 5/2. Any questions, any issues? Everybody good with that? What about for 3x to the negative 2? The first derivative should be what? Should be negative 6x to the negative 3. And the second derivative should be 18x to the negative 4. Third derivative should be negative 72x to the negative 5. And the fourth derivative should be 360x to the negative 6. If we wanted to, we could write each of those as over x cubed, over x to the 4th, over x to the 5th, and over x to the 6th, but no particular need to do that. Everybody good? All right. Let's see, product rule. Product rule and quotient rule, we know those are important. I know we proved them last year, so I'm not going to bother to prove them today, even though I've got it written here. We know the product rule is u times the derivative of v plus v times the derivative of u. All right, so anytime you have a product of two functions, you have to use the product rule, u dv plus v du. Okay. And we won't worry about proving it today. If you want to, remember how to prove it, just go online find a video of it. It should be pretty easy to find. If I can find one that proves it on College Board, I'll assign that to make you watch it. But all right, so obviously we could take this one and we could distribute it all out and then take the derivative, but we could also use the product rule. So just for practice sake, let's use the product rule. We should start with u, and then the derivative of v, which is what? Should be 2x, good, and then plus our v, x squared plus 3, times our derivative of u, which is 3x squared. And as far as I'm concerned, that's a good enough answer. But if you want to simplify it all out and make this 2x to the 4th plus 2x plus 3x to the 4th plus 9x squared and combine it together, that's good too. Either way you want to do it, it's fine with me. And if we distribute it out first and then taking the derivative, we should get the exact same thing. Everybody good with that? All right, I'm not going to prove the quotient rule. We did that last year also. But quotient rule, v du minus u dv all over v squared. So you want to make sure you have the quotient rule memorized. Make sure you know the quotient rule and can apply it. Anytime you have a quotient of two functions, you can apply the quotient rule. So this should be, if we're looking for f prime, this should be v du minus u dv all over v squared. And we'll end up with 2x cubed plus 2x minus 2x cubed plus 2x all over x squared plus 1 squared, or 4x over x squared plus 1 squared. Everybody good with the quotient rule there? Everybody all right? Easy enough? And the reciprocal rule, which is just a special case of the quotient rule. So if I want to take the derivative of 1 over a function, it's the opposite of the derivative of the function divided by the function squared. And if we were to go through and use the quotient rule for this, we'd see that it should be v g of x times the derivative of u, which is 0, minus u, which is 1, times the derivative of the denominator all over the denominator squared. And this first term cancels, and we got negative g prime over g squared. So it's just a kind of sort of shorthand for quotient rule when it's a 1 over, or it could be 2 over, 3 over, and this number here is just a 2 or a 3. Everybody good? And I know this is all review and we're kind of going through it real quick, but just want to make sure we talk about it all for just a minute, just so we haven't forgotten it all. So using the reciprocal rule, what's f prime? Should be negative g prime, which is 6x squared plus 5 over that denominator squared. Everybody good? All right, and we'll remind ourselves of the 4 reasons why the derivative at a point might not exist. The first of those is a corner, like an absolute value graph. The second one is a cusp. like in the graph of x to the 2/3. Next one is a vertical tangent, like that graph of x to the 1/3. And then the last would be a discontinuity, which I don't have a picture of, but I think you know what a discontinuity looks like. The corner cusp, vertical tangent, or a discontinuity are the reasons why a derivative might not exist. So make sure you remember that and how to get these different things. And in fact, we're going to deal a lot with the cusps this year, especially when we start talking about polar functions. Same with some vertical tangent lines with polar and parametric functions. We'll see those a little bit more often. So be prepared for that. And one thing they like to do on the AP test is give you a whole bunch of values and then ask you to just apply one of the rules. So if I want to find y prime of 2, if y is equal to uv, then that should be u of 2, v prime of 2, plus v of 2, u prime of 2. So we should just be able to plug in the numbers 3 times 2 plus 1 times -4 and get 2. And if we were doing u over v, then that should be v u prime minus u v prime over v squared. So in this case, that'll be 1 times -4 minus 3 times 2 all over v squared, which was 1. uv prime, yeah, Molly, that's fine, yeah. Either way you want to write it is good. Everybody good with those? Product rule, quotient rule, reciprocal rule, places where the derivative is undefined. All right, moving on. Chain rule, right? Hopefully you all remember the chain rule. Right. We use the chain rule when we have a composition of two functions. So dy dx for a composition of two functions is equal to dy du times du dx, or we might write it as f prime of u times g prime of x, or just f prime of g times g prime. All the different notations for the chain rule, but remember that these are when you have a function within another function. So a composite function, a composition of two functions. Something like sine of 2x. So we'll real quickly use the chain rule on this, and then we'll also use the trig identity to show that they come out to be the same. So our substitution, which I'm only going to write out these substitutions for today probably, and then from now on I won't write out the substitutions for the chain rule. I'll just expect you to be able to do them, but we'll do the substitution where u is equal to 2x, and that makes du equal to 2. And so, or du dx we'll say is equal to 2. And so using the chain rule, the derivative of y, the derivative of sine should be cosine. It'll be cosine of 2x, and it's times the derivative of u, which was 2. So it should come out to be 2 cosine 2x. Right, if we have y equals sine u with u equal to 2x. But we could write this out as 2 sine x cosine x and use the product rule. So 2 sine x times negative sine x plus 2 cosine x times cosine x, which is negative 2 sine squared x plus 2 cosine squared x, or 2 cosine squared x minus 2 sine squared x, which is 2 times cosine squared minus sine squared, which is the double angle identity for cosine that you should be familiar with. So it comes out the same either way, but obviously the chain rule is a lot less work. Everybody good with the chain rule part? All right. We'll remember that the derivative of position is velocity, derivative of velocity is acceleration. So if we're looking for the velocity function given this position function, we need to take the derivative of cosine t squared plus 1. So using the chain rule, that should be, what's the derivative of cosine of u? Should be negative sine of u, and then times the derivative of u. So this will be times 2t. Everybody good with that? All right, what should the derivative of this be? This is sine of u. So the derivative of that should be cosine of u. And we're going to multiply it by the derivative of u, 2x plus 1. Any questions or issues on that? Everybody still good? All right, what about this one? We should know that the derivative of root u is 1 over 2 root u. And we need to multiply it by the derivative of u, which is 2x. So we end up with just x over root x squared plus 1. Everybody still good? I'm going to assume so, even though nobody is responding.
Yes.
All right. Should all be review easy. Just want to put it all back in your brains. Because if we get to the more complicated stuff and you can't do the easy stuff, we're going to have a problem. So what about this one? This is u to the negative third power, isn't it? So we should do negative 3 u to the negative fourth power. So we can put that 4x squared plus 6x minus 7 to the fourth down here. And then we need to multiply by the derivative of u, which is 8x plus 6. And if you want to factor out the 2 from the numerator and make it a negative 6 times 4x plus 3, that's great, but no real reason to do that. Everybody good? All right. All right, so here we'll have to use the product rule and the chain rule in conjunction with each other. 3x plus 1 to the 6th times the square root of 2x minus 5. That shouldn't be conceptually too difficult, just a little bit messy. We've got u, 3x plus 1 to the 6th times the derivative of root 2x minus 5, which is 1 over 2 root 2x minus 5, times the derivative of 2x minus 5, which is 2, plus your root 2x minus 5 times the derivative of 3x plus 1 to the 6th, which is 6, times 3x plus 1 to the 5th, times the derivative of 3x plus 1, which is 3. And we can cancel stuff out here. 3x plus 1 to the 6th over root 2x minus 5 plus 18 root 2x minus 5 times 3x plus 1 to the 5th. Any questions or issues on that one? Gets a little more complicated as we add in rules within rules, but Hopefully not too bad. Just got a couple more, then we'll let you guys go here. So what about tangent cubed 4x? What's the outermost function on this? It's the cubed, right? So this is u cubed with u equal to tangent 4x. So we should get 3u squared, 3 tangent squared 4x times the derivative of u, but the derivative of u, the derivative of tangent 4x, should be 4 times the derivative of tangent x, which is, we should remember, 4 secant squared 4x. And so I'm not going to go through and do all the proofs for all of the trig derivatives like we did last year, but I will post up the formula sheet for all of the derivatives that you should be knowing for this class, and that'll include all the trig ones. So if you don't remember all the trig derivatives, memorize them again. If you don't remember all the inverse trig derivatives, memorize them again. And log derivatives, memorize them again. Exponential derivatives, memorize them again. Everybody good? All right. Last one. We want to show that the slope of every line tangent to the curve y equals 1 over 1 minus 2x to the third power is positive. So if we're looking at the slopes of the tangent lines, we need to take the derivative. So what's y prime going to be? This is u to the negative 3. So that should become negative 3 u to the negative 4 times the derivative of u, which is negative 2, giving us 6 over 1 minus 2x to the 4th. And we know that 6 is always positive, and we know that anything being raised to the 4th power is always positive unless that thing is 0. And if this thing was 0, then we wouldn't have a point on our original function, because if 1 minus 2x makes the derivative equal to 0, it's also going to make the original function equal to 0 in the denominator there. Any questions or issues with that?
Can you just verbally explain the why it's positive part one more time?
Yeah, so I mean, 6 is positive, right? And anything being raised to the 4th power is also positive. So no matter what, this derivative is a positive divided by a positive. And the only case in which this denominator is not positive is when 1 minus 2x equals 0, right? So that'd be when x is a half. But there are no points on our original function where x equals a half anyway, because there's a vertical asymptote there. So don't have to worry about that one. Is that good?
Yes, thank you.
Yep. Any questions? All right. I'm going to let you go. I'm going to post up a brief assignment on using the difference quotient and a limit to find a derivative. And then I'm also going to post up later this afternoon an assignment just with the basic derivatives, just to make sure you got them all. The limit one I'm going to have due today. It's like 5 questions, so it shouldn't take you too long. You could probably get it done if I get it posted right away. Probably have it done close to before your next class starts. The other one will be due tomorrow, but it should be basic stuff.